Hello, my name is Haiwen Zhang, and my paper is on the Copenhagen interpretation and its alternative theory in quantum mechanics. This is a report video on my essay. Okay, first, I'm going to provide you with a general overview of my essay. The essay is divided into two sections: the conflict between substantiality and completeness in quantum mechanics, and the relationship between causality and observation. Since the Copenhagen interpretation is the most orthodox explanation, this paper will focus on this particular theory and offer some of its own alternative theories. We will see how those alternative theories are disproved by fellow scientists. The essay aims to clarify and systematize the historical development of quantum mechanics, showing the current progress of quantum mechanics. Quantum mechanics is a new perspective of physics in the 1900s. Before the 1900s, the physics world was dominated by classical mechanics led by Isaac Newton and James Maxwell. However, soon people realized that classical mechanics couldn't be enough because there was too much that could not be explained. After the 1900s, quantum mechanics flourished. It arose from the unresolved questions in classical mechanics and describes physical properties at an atomic or subatomic scale. However, controversies are still unresolved. Physicists use quantum mechanics equations to predict subatomic phenomena, but the underlying mechanism remains unknown. In fact, there is no single interpretation of quantum mechanics that has gained consensus agreement from scientists. The Copenhagen interpretation is the most orthodox explanation of all the theories. In this paper, the Copenhagen interpretation provides a rational and elegant explanation for two conflicts mentioned in the essay. Let us first examine the conflict between substantiality and completeness. The famous Schrödinger equation describes the particle's wave function, which states the following on the PowerPoint. It is the quantum counterpart of Newton's second law in classical mechanics. Unlike classical mechanics, the wave equation is spread out in space instead of localized at a point. This indicates that quantum mechanics is a study of uncertainty. Born's rule provides us with an exact formula to calculate the probabilities, which is as written. The Born rule introduces indeterminacy to quantum mechanics, which means that quantum mechanics cannot yield a specific result of a simple experiment. Physicists and philosophers were extremely bothered by the thought that people may live in a fundamentally indeterministic world. Heisenberg's uncertainty principle reveals how this is distributed in the quantum realm. It states the following. In this principle, the x represents the uncertainty in the position and the p represents the uncertainty in the momentum. The two values are in conjugate space. When the position becomes more precise, the momentum becomes more uncertain, and vice versa. Now let's move on to possible theories of this phenomenon. This essay provides two theories that address this conflict. The first is Einstein's local hidden variable theory and the EPR paradox. Suppose that the quantum realm is complete. So can it be substantial as well? A possible explanation is that when not measured simultaneously, the position and momentum can both be known at separate times. The EPR paradox addresses this rejection. Suppose there are two entangled systems. When measuring the position of the particle in system A, the wave function of the position space collapses with the measurement. The wave function of the position space for particle B also collapses because the two systems are entangled. The measurement of system A causes the position of system B to be substantial, and the momentum of system B is immeasurable. This means that the determinacy of system B depends on system A. However, Einstein cannot accept this unnatural situation. He believes that completeness should be abandoned and substantiality should remain, suggesting that there is no way for both position and momentum to be substantial. Einstein's local hidden variable theory proposed states that there is a local hidden variable inside particles A and B, so their states are predetermined before measurement. There is no determinacy between system A and B, so the conflict is explained. Another explanation is the focus of our essay, the Copenhagen interpretation. Before measurement, all particles exist in a superposition state, which means that the physical quantities such as the angular momentum, position, and spin are unknown and unknowable until measurement. The particles are in a superposition of multiple states. A particle can be here and there at the same time. After measurement, people cannot observe a particle in its superposition state, but can only observe it in one state. As stated in the previous section, the wave function is used to describe the particle's state and calculate the probability of finding a particle at a certain point. According to Heisenberg's uncertainty principle, the momentum and the position of the particle are in conjugate space. Upon measurement, the probability lies entirely on one eigenstate, which is 100%, and the probability of the other is undetermined, which is 0%. For example, when the position is measured, the momentum of the particle becomes more uncertain and vice versa. When measured, the wave function collapses and can no longer describe the quantum system. Therefore, it is said that measurement disrupts the quantum system. The difference between the Copenhagen interpretation and Einstein's local hidden variable theory is that the former denies the existence of a hidden variable and claims that the quantum system is substantial, while the latter acknowledges that completeness of the quantum system exists. So which theory is correct? Both theories seem to be reasonable until John Stuart Bell has come up with a simple inequality to resolve the conflict. Bell's inequality is stated as shown in the PowerPoint. However, in Einstein's local hidden variable theory, Bell's inequality is written as the square root of 2 is larger or equal to 1, which means that Bell's inequality does not apply under the EPR theory. Therefore, Bell's inequality has proved that the Copenhagen interpretation is correct. Okay, now let's move on to the second topic, which is the issue concerning causality and observation in quantum mechanics. The key to this topic is the wave-particle duality started since the double-slit experiment, which I am not going to extend further here. The issue was again highlighted in Wheeler's delayed choice experiment. The experimental setup of the experiment reveals whether the particle or wave nature of a quantum system is determined before or after the system has entered the apparatus. Let's take a look at the picture on the right. Wheeler's delayed choice experiment is designed as the following. The photon emitter is at the left top of the drawing and releases photons in an unknown state of either wave or particle. A photon has entered the quantum system when it enters BS1. At the right top and left bottom of the drawing, there are two reflectors used to reflect the photons at an angle of 90 degrees. At BS2, there is a beam splitter. The experimenter can choose whether to remove the beam splitter at BS2. At the end of paths D and E lies two detectors to detect the state of the photons. It is shown that if the beam splitter exists at BS2, then interference will be detected by the detectors, which means that the photon behaves as a wave. However, without BS2, the photon behaves as a particle since the detector at the end of paths D and E randomly detects the photon, which means that the probabilities of the particle choosing paths B or C are the same, which is both 50%. Now Wheeler decides to answer the question, during which state in the experiment does the photon decide its state as either wave or particle? Suppose the experiment begins without the beam splitter at BS2. The photon will behave as a particle since it assumes that the second beam splitter does not exist. Common sense would suggest that the photon will continue to act as a particle even when the experimental setting changes. The state of the particle is predetermined, and it will go down the path it has chosen when emitted. However, when the beam splitter is popped up at BS2, the photon changes its state to waves by changing its path because the detector has detected interference. The photon behaves as if the second splitter has already been there the whole time. The phenomenon proposes an interesting question. Can our choice change the past? The causality seems reversed in the quantum realm. Now let's look at some probable explanations for Wheeler's delayed choice experiment. The first one comes from Wheeler himself. He believes that the findings do not mean the present choice can influence the past. Rather, he thinks that the past has no existence until it is recorded in the present. There is no past until the point where you can make the measurement in the present, and thereby the past comes along with the present. The second explanation is the Copenhagen interpretation. According to the Copenhagen interpretation, it is impossible and meaningless to visualize the quantum process. Making a sharp separation between the properties of the observed system and the observing apparatus would also be impossible. Bohr once wrote, "In any attempt of a pictorial representation of the behavior of the photon we would thus meet with the difficulty to be obliged to say, on the one hand, the photon always chooses one of the two ways, and on the other hand, that it behaves as if it passed both ways." The central explanation of the Copenhagen interpretation is that scientists should just calculate based on the quantum phenomena without asking questions, because it is futile to visualize the quantum process. The last interpretation is the Bohm interpretation. In Bohm's interpretation, there is a global hidden variable behind the quantum system. The particle is always under the law of classical mechanics unless it is placed in the quantum system where a global hidden variable is controlled. The central idea of Bohmian mechanics is that the system of particles is deterministic and is deterministic by the wave function. As in the double-slit experiment, the photon acts under the law of classical mechanics and has a definite trajectory passing through one of the two slits. The slit through which it passes depends wholly upon its initial position and wave function. There is no uncertainty in quantum mechanics, but rather the past is already predetermined. In Wheeler's delayed choice experiment, the photon stays as a particle until it detects the presence of the other beam splitter and changes to a wave. However, the Bohmian interpretation is refuted because it is inconsistent with general relativity. The Bohmian mechanics cannot describe fast particles close to the speed of light. Still, the Bohmian mechanics fail to give theoretical updates compared to the Copenhagen interpretation, but rather it accords with the common knowledge of classical mechanics. To sum up, the Copenhagen interpretation has elegantly explained two of the largest conflicts in quantum mechanics, which is the conflict between substantiality and completeness, and the issue concerning causality and observation. Some other explanations are also included. Despite their weaknesses compared with the Copenhagen interpretation, it is still believed that it is worthwhile to explore them in depth. but that does not mean that the Copenhagen interpretation does not have flaws. The Copenhagen interpretation fails to provide the descriptions of the collapse of wave functions. It does not explain whether the collapse is instantaneous or continuous. It also fails to give a clear definition of causality. Therefore, more work should be focused on the refinement of the Copenhagen interpretation. This is the end of my report. Thank you for listening.